Refraction of light. Light seems to travel along straight line paths in a transparent medium. But what happens when light enters from one transparent medium to another? Place a thick glass slab over some printed matter. We observe the letters appear raised when viewed through the glass slab. Similarly, when a pencil is partly immersed in water in a glass tumbler, it appears to be displaced at the interface of air and water. Even a coin kept in water in a glass tumbler appears to be raised when viewed from the sides. Is this some kind of a trick? No, there is no trick involved. It is based on a purely scientific phenomenon. Let us consider the case of the apparent displacement of a pencil partly immersed in water. The light reaching from the portion of the pencil inside water seems to come from a different direction compared to the part above water. This makes the pencil appear to be displaced at the interface. The extent of the effect is different for different pair of media. It appears that when traveling obliquely from one medium to another, the direction of propagation of light in the second medium changes. This phenomenon is known as refraction of light. Snell's law. We know that light travels in a straight line through any medium of uniform density. However, the speed of light depends on the nature of the medium in which it travels. Distance moved by light in a given time in different media. When light travels from a rarer medium to a denser medium, its speed decreases. Whereas, speed of light increases when it travels from a denser to a rarer medium. It is due to this change in the speed of light that the ray of light bends as it goes from one medium to another. Thus, the change of speed of light as it travels from one medium to another is the cause of refraction. Refraction occurs right at the interface of the two media, and the angle of bending of a ray would depend upon difference of speeds of light in two media. AO is called incident ray. OB is refracted ray. NON dash is called normal to the plane surface XY, separating the two media. Angle of incidence represented by I. Angle of refraction represented by R. Angle for refraction R is never equal to angle of incidence I except for normal incidence. The incident ray, the refracted ray and the normal at the point of incidence all lie in the same plane. In fact, the ratio of sine of the angle of incidence to the sine of the angle of refraction is a constant for the light of a given color and for the given pair of media. This law is also known as Snell's law of refraction after the name of its discoverer, Willebrord Snell. And this constant is called the refractive index of the second medium with respect to the first. The direction of the bending of light depends upon the optical density of the two media. In going from an optically rarer to a denser medium, the ray of light bends towards the normal. When light travels from an optically denser to a rarer medium, it bends away from the normal. When light is incident normally on a boundary of two media, no change in direction of light occurs. No refraction occurs at the boundary that separates two media of equal refractive index. Laws of refraction. In order to get a practical feel of the concept, let us do an activity using a rectangle glass slab. Fix a sheet of white paper on a drawing board using drawing pins. Place a rectangular glass slab over the sheet in the middle. Draw the outline of the slab with a pencil and let's name the outline ABCD. Take 4 identical pins. Fix 2 pins, say E and F, vertically such that the line joining the pins are inclined to the edge AB. Look for the images of the pins EF through the opposite edge. Fix 2 other pins, say G and H, such that pins and images E and F lie on a straight line. Remove the pins and the slab. Join the position of tips of the pins E and F and produce line up to AB. Let EF meet AB at O. Similarly, join the position of tip of the pins G and H and produce P up to the edge CD. Let HG meet CD at O'. Join O and O'. Also EF up to P. Draw perpendicular N to AB at O and M perpendicular to CD at O'. Now here, you can easily note that the ray of light has changed its direction at point O and O'. O and O' are the points that lie on surface separating two transparent media. The light ray at point O has entered from a rarer medium to a denser medium, from air to glass, and has bent towards the normal. At O', the light ray has entered from glass to air, that is, from a denser medium to a rarer medium, and the light has bent away from the normal. EO is the incident ray, OO' is the refracted ray, O'(H) is the emergent ray. The extent of bending of the ray of light at the opposite parallel faces AB and CD of the rectangular glass slab are equal and opposite, and therefore the emergent ray is parallel to the direction of the incident ray. This experiment also verifies the two laws of refraction, that is, 1. The ratio of the sine of the angle of incidence to the sine of the angle of refraction for a particular pair of media is constant for the light of a given color and for the given pair of media. 2. The incident ray, the refracted ray, and the normal to the interface of two transparent media at the point of incidence all lie in the same plane. Lenses. We know that glasses used in spectacles and in magnifying glasses to see tiny parts are different from the usual mirrors used in our daily life. Lenses are used in photographic cameras, telescopes, microscopes, theater spotlights, projectors, etc. In fact, a spherical lens is a piece of transparent refracting material, usually glass, which is bounded by two curved surfaces or by one curved and one plane surface. May formation of images by lenses. Spherical lens. Convex lens is a converging lens which is thick at the center and thin at the edges. Concave lens is a diverging lens which is thick at the edges and thin at the center. Now the question arises, how do lenses form images? What is the nature of the image formed? These lenses form images by refracting light. The center point of a lens is called its optical center. A ray of light passing through the optical center does not suffer any deviation. The aperture of a lens is the diameter of the circular edge of the lens. An imaginary straight line passing through the center of curvature of the two surfaces of the lens is called principal axis of the lens. Now we will learn about the formation of images by the lenses. Let's take a convex lens first. Firstly, find the approximate focal length of the lens by focusing light of the sun on a piece of paper. A convex lens has two surfaces and hence it has two principal foci or two focal points. First principal focus, represented by the f1 of a convex lens, is the position of a point object on the principal axis of the lens, for which the image formed by the lens is at infinity. The distance of first principal focus of the lens from the optical center is called first focal length of convex lens. Second principal focus of a convex lens, represented by f2, is the position of an image point on the principal axis of the lens when the point object is situated at infinity. The distance of second principal focus of the lens from the optical center of the lens is called the second focal length of convex lens. Now, place the lens on an optical bench. Place it on the central line such that the optical center of the lens lies just over the line. Place a burning candle on one side of it. First, the candle is placed far behind the 2f1, that is at infinity. The image is formed at the focus of the other side, that is f2, and it is highly diminished, point-sized, real and inverted. Now, if the candle is placed just beyond 2f1, observe the image. Image is formed between focus, f2, and center of curvature, 2f2 on the other side, and is diminished, real and inverted. Now the candle is placed at 2f1. And when screen is adjusted for a clear sharp image, what do you observe? Image is formed at 2f2 and of the same size and is real and inverted. Now, place the candle between f1 and 2f1. And the image is formed beyond 2f2 and is enlarged, real and inverted. Now, place the candle at focus f1 The other image is formed at infinity, highly magnified, real and inverted. Now place the candle between focus f1 and optical center O. Now the image is formed beyond f1 on the same side of the lens as the object and is enlarged, virtual and erect. Choosing the rays for image formation in lenses. Ray passing through optical center of the lens passes straight after refraction through the lens without any deviation. Ray passing through first principal focus of the convex lens, incident on the lens, becomes parallel to the principal axis of the lens after refraction. In case of concave lens, a ray of light appearing to meet at the principal focus of a concave lens after refraction will emerge parallel to the principal axis. It is important to note that the image is formed at a point where any two of the refracted rays actually meet or appear to meet. Image formation by convex and concave lens. Part 1. Now let's understand the image formation in lens using ray diagrams. Ray diagrams will also help us to study the nature, position and relative size of the image formed by lenses. A lens forms the image of an object placed in front of it. Any point on the object acts as a point source from which an infinite number of rays start. The rays suffer refraction on passing through the lens. 1. From the object, incident on the lens parallel to the principal axis after refraction through the convex lens passes through principal focus on the other side of the lens. 2. A ray of light passing through a principal focus after refraction from a convex lens will merge parallel to the principal axis. 3. A ray of light passing through the optical center of a convex lens will emerge without any deviation. 1. In case of a concave lens, the ray appears to diverge from the principal focus located on the same side of the lens. 2. A ray of light appearing to meet at the principal focus of a concave lens after refraction will emerge parallel to the principal axis. 3. A ray of light passing through the optical center of a lens will emerge without any deviation. Image formation by convex and concave lens. Part 2. When the object is at infinity, rays starting from the object diverge, but on traveling such a large distance, are assumed to become parallel while falling on the lens and converge on refraction. The ray passing through the optical center of the lens goes undeviated. The refracted rays meet at a point on the other side. Thus, the real image of object is formed at second principal focus f2 of the convex lens. Here we conclude that when the object is at infinity, the image is 1. At second principal focus of the lens, 2. Real and inverted, 3. Highly diminished, that is, image is much smaller in size than the actual object. When the object is held beyond 2f1, a ray of light starting from top and incident on the lens in a direction parallel to the principal axis of the lens, on refraction passes through second principal focus f2 of the lens. Another ray starting from top and incident of the lens goes undeviated through the optical center of the lens. The two refracted rays meet actually at A dash to form the full image of the object. A real and inverted small image is formed. The position of the image formed is between f2 and 2f2 on the other side of the lens. Thus we conclude that when the object is held beyond 2f1, the image is 1. Real and inverted, 2. Smaller in size than the object. When the object is held at 2f1, a ray of light starting from top and incident on the lens in a direction parallel to the principal axis of the lens on refraction passes through second principal focus f2 of the lens. Another ray starting from A and incident on the lens through optical center so goes undeviated. The two refracted rays actually meet on the other side of the lens and the image is 1. Formed at 2f2, 2. Real and inverted, 3. Of the same size as the object. Similarly, when the object is held between f1 and 2f1, the image is formed beyond 2f2 on the other side of the convex lens, real, inverted, and larger in size than the object. When the object is at f1, the image is formed at infinity on the other side of the lens, real and inverted, highly magnified. When object is placed between f1 and the lens, the image is formed on the same side of the lens beyond f1, virtual and erect and magnified. This table gives a summary of nature, position, relative size of the image formed by a convex lens for various positions for the object. Students, this table is very important from the examination point of view, so your utmost attention is required. Now let us repeat the activity with the concave lens and observe the image formed. Formation of image by a concave lens when the object is at infinity. When the object is moved away from the concave lens, the image becomes smaller in size and moves towards the principal focus of concave lens. When the object is at infinity, the image is formed at the principal focus on the same side of the lens as the object. The image is virtual, erect, and highly diminished to almost point size. The object lies between optical center and infinity. A ray of light starting from the top point of the object falls on the concave lens in a direction parallel to principal axis of the lens. This ray diverges and on producing back, it appears to come from the principal focus located on the same side of the lens. Another ray of light starting from the same point on the object passes undeviated through the optical center. The two refracted rays intersect at A dash to form a virtual image of the object. Hence we conclude that when an object is held anywhere between optical center of the concave lens and infinity, the image formed is 1. Between optical center and the principal focus located on the same side of the lens as the object is 2. Virtual and erect, and 3. Smaller in size than the object. Very important to remember that a concave lens always gives a virtual, erect, diminished image irrespective of the position. lens formula and magnification. As we have a formula for spherical mirrors, we also have a formula for spherical lenses. This formula gives the relationship between object distance, u, image distance, v, and the focal length, f. The lens formula is expressed as 1 upon v minus 1 upon u is equal to 1 upon f. The lens formula given here is general and is valid in all situations for any spherical lens. However, it is very important to take proper care of the signs of different quantities while putting numerical values for solving problems relating to lenses. Now let us learn about the concept of magnification. Magnification. The magnification produced by a lens, similar to that for spherical mirrors, is defined as the ratio of the height of the image and the height of the object. It is represented by the letter m. If h is the height of the object and h dash is the height of the image given by a lens, then the magnification produced by the lens is given by m is equal to height of the image upon height of the object is equal to h dash upon h. Magnification produced by a lens is also related to the object distance u and the image distance v. This relationship is given by magnification m is equal to h dash upon h is equal to v upon u. To understand this concept better, let us take some examples. A concave lens has a focal length of 15 centimeters. At what distance should the object from the lens be placed so that it forms an image at 10 centimeters from the lens? Also, find the magnification produced by the lens. Let us try to solve this. We know that a concave lens always forms a virtual, erect image on the same side of the object. From the question it is given, image distance v is equal to minus 10 centimeters, focal length f is equal to minus 15 centimeters, object distance u is equal to unknown. Since 1 upon v minus 1 upon u is equal to 1 upon f, it will be 1 upon minus 10 minus 1 upon u is equal to 1 upon minus 15. On solving, this comes out to be 1 upon u is equal to minus 30, or u is equal to minus 30 centimeters. Thus, the object distance is 30 centimeters. Now in order to find the magnification M is equal to V upon U. M is equal to minus 10 centimeters upon minus 30 centimeters is equal to 1 upon 3 is equal to plus 0.33. The positive sign shows that the image is erect and virtual. Hence we find that the image is 1/3 of the size of the object. Power of a lens. In the previous modules, we have already studied that the ability of a lens to converge or diverge light rays depends on its focal length. For example, a convex lens of short focal length bends the light rays through large angles. By focusing them closer to the optical center. Similarly, concave lens of very short focal length causes higher divergence than the one with the short focal length. The degree of convergence or divergence of light rays achieved by a lens is expressed in terms of its power. The power of a lens is defined as the reciprocal of its focal length. It is represented by the letter P. The power P of a lens of focal length f is given by P is equal to 1 upon f. Many optical instruments consist of a number of lenses. They are combined to increase the magnification and sharpness of the image. The net power P of the lenses placed in contact is given by the algebraic sum of the individual powers P1, P2, P3 and so on, as P is equal to P1 plus P2 plus P3 plus so on. Students, do you know, the use of powers instead of focal lengths for lenses is quite convenient for opticians. During eye testing, an optician puts several different combinations of corrective lenses of known power in contact inside the testing spectacles frame. The optician calculates the power of the lens required by a simple algebraic addition. For example, a combination of two lenses of power plus 2.0D and plus 0.25D is equivalent to a single lens of power plus 2.25D. The simple additive property of the powers of lenses can be used to design lens system to minimize certain defects in images produced by a single lens. Such a lens system, consisting of several lenses in contact, is commonly used in the design of camera lenses and the objectives of microscopes and telescopes. Uses of concave and convex mirrors. Concave mirrors are commonly used in torches, searchlights, and vehicle headlights to to get powerful parallel beams of light. They are often used as shaving mirrors to see a larger image of the face. The dentists use concave mirrors to see larger images of the teeth of patients. Large concave mirrors are used to concentrate sunlight to produce heat in solar furnaces. Uses of convex mirrors. Convex mirrors are commonly used as rear viewing mirrors in vehicles. These mirrors are fitted on the sides of the vehicle, enabling the driver to see traffic behind him or her to facilitate safe driving. Convex mirrors are preferred because they give an erect, though diminished image. Also, they have a wider field of view as they are curved outwards. Thus, convex mirrors enable the driver to view much larger area than would be possible with a plane mirror.